Okay, we're going to now continue section 7.3, trigonometric substitutions. The video had stopped and I wasn't able to continue with that video, so we're going to have a two-part video. There's not that many problems left. There's one, two, three, four problems left for us to work out. So here we are. We're looking at the integration of dx over the square root of x squared minus 9. We could say that u is equal to x, a is equal to 3, and that means that we have x is equal to 3 secant theta, because this is in the form, right? This is in the form of u squared minus na squared. All right, so if x is equal to 3 secant theta, then dx is equal to 3 secant theta tangent theta d theta. And that's what we were doing before. Oh, and one other thing, where if x is equal to 3 secant theta, then secant theta is equal to x over 3. And let's draw our triangle real quick. There's my theta, x, 3, the opposite side, it's x squared minus 9. So we're going to do our substitution as we've done in the previous slides. So instead of a dx, we write 3 secant theta tangent theta d theta. Instead of x squared, we're going to have 3 secant squared, which gives me a 9 secant squared theta minus 9, and that's all taking the square root of it. We will simplify this. So we have a 3 secant theta tangent theta d theta. 9 secant squared theta minus 9, I can factor out at 9. The 9's a perfect square, so that's going to come out. Leaving behind secant squared theta minus 1. We can then cancel out, right? We can cancel out the 3's and rewrite what's in the square root. Secant theta tangent theta d theta. Instead of secant squared theta minus 1, let's write a tangent squared theta. Take the square root of that. Then from there, the square root of tangent squared theta is just tangent theta. So in the numerator, I still have a secant theta tangent theta d theta. Now I have a tangent theta in the denominator, which again, we can cancel that tangent theta with that, leaving us with secant theta d theta. So with that, we would have to go back to the chart, to that page that has all our integrations that I'm going to give you for the test, and we should then see, and after a while remember, that the integration of secant theta is the natural log of secant theta, or the absolute value of secant theta plus tangent theta. Let's write this a little nicer. Plus a constant. We would then go back to our triangle that we have up here and look for what is a tangent theta, what is a secant theta, and then we'd find out that after substitution, we have the natural log of the absolute value of x plus x over 3 plus the square root of x squared minus 9 all over 3 plus a constant. We can then rewrite it if we'd like to be one fraction. And if you really want to go crazy, you can use the rules of logs and break this apart. And yes, I did put an absolute value around the 3, and I did not need to because 3 is a positive number, and I could just drop the absolute value symbol. I'll be honest, I would accept any, obviously I would accept all 3 of these answers, but the first answer for this problem would probably be good enough. All right, you've done a lot of work at that point. I think I can accept that. So we're going to look at this problem. I have an x cubed over a 4x squared plus 9 raised to the 3 halves dx. Well, let's look what we have. We're going to let u this time is equal to 2x, not 4x squared, or not x. a is equal to 3. So it looks like we're in the form of a u squared plus an a squared, which means we're using tangent theta. So we could say that 2x is equal to 3 tangent theta, or we could say x is equal to 3 halves tangent theta. For what we need with it, we'll take the derivative of both sides. Dx is equal to 3 halves secant squared theta d theta. But based off of this one here, we say that tangent theta is equal to 2x over 3. From that, we could build our triangle. The opposite side's 2x. This is 3. This is 4x squared plus 9. I don't know if we've caught on to this, but this has always been the missing side. And hopefully we're seeing that. So it really isn't hard to build our triangles. Now, we're going to substitute everything. Instead of an x cubed, we're going to take the x value and cube it. So I have a 3 halves cubed tangent cubed theta all over 4 times, and I'm going to break up the 3 halves again, squared tangent squared theta plus 9. That's all being raised to the 3 halves. Instead of a dx, I have a 3 halves secant squared theta d theta. Now we're going to clean this up some, keep what we can and factor out what we can. And to save some time, I'm just going to go to that next step. So we have 27 over 8 tangent cubed theta. I have a 27 tangent squared theta plus 1 raised to the 3 halves times 3 halves secant squared theta d theta. From here, I can start canceling out some things, hopefully, or at least rewrite it. Instead of a tangent squared theta, I can write that as secant squared theta. So, oops, I lost something here, sorry. 27 over 8. So I have a secant squared theta to the 3 halves. 3 halves secant squared theta d theta. Now what's interesting is this part here. I have a secant squared theta raised to the 3 halves. Well, if I have that, that's the same thing as having you multiply the exponents, and that just gives me secant theta. So instead of writing it this way, we're going to write 27 over 8 tangent cubed theta, 27 secant cubed theta, 3 halves secant squared theta d theta, and we're going to cancel out a lot of terms at this point. Before I start canceling out, a little side note here, I have a 27 over 8. I need to multiply by 1 over 27, and I also need to multiply by 3 halves, which is equal to 3 over 16. That's taking care of all the constants that we have in this problem. So all I did was take this, this, and this, and now I'm going to replace it with this. 3/16. So I have 3/16 on the outside. If I have a secant squared theta, secant cubed, this goes away. So I really have a tangent cubed theta over secant theta d theta. And then I can rewrite all this. I can't integrate the way it is, so I'm going to rewrite this in terms of sines and cosines. So I still have a 3/16. Instead of tangent theta, tangent cubed theta, I have a sine cubed theta over cosine cubed theta. Instead of a 1 over secant theta, that's just times a cosine theta d theta. Well, that now allows me to get rid of a few more terms and get rid of this cosine, and that cosine cubed is now cosine squared. So we have 3/16 sine cubed theta over cosine squared theta d theta. Now I can look at sine cubed theta and I can rewrite that because remember the last section we wanted to get everything, if we had an odd number, siphon off that and leave one sign, so we could do that u substitution. So we're going to look at trying to do a u substitution. This is 3/16. Instead of sine cubed, it's a sine squared. I'm going to write it as 1 minus cosine squared theta. Right, that's my sine squared theta. There's my sine theta. Give me the sine cubed that I need in the numerator. Cosine squared theta d theta. I can say let u equal cosine theta. Du is equal to minus sine theta, or minus du is equal to sine theta. Now I have everything I can use to substitute. So I have a 3/16, 1 minus u squared, all over u squared, du. So that can be broken up to 3/16, 1 over u squared, that's an easy one to integrate, minus u squared over u squared, that's just 1 du. Through integration, I have 3/16 times a minus 1 over u minus u plus a constant. But we didn't start off with u. We want to be in sines and cosines, or we want to be in, we'll go back to u substitution, which is cosine, so I have 3/16 minus 1 over cosine theta minus cosine theta plus a constant. Instead of writing minus 1 over cosine theta, we'll rewrite it as secant theta negative. And I lost a negative. Oh, I lost my negative somewhere. I did my u substitution. I'm going to do this in a different color so you can see where I lost it. We did the u substitution. Remember, there was a negative here. So I'm putting that in blue so we can clearly see where I missed it. So now you can see where I've made that mistake. Secant theta minus cosine theta plus a constant. Now that we have it, we can go back into our triangle, which hopefully we drew up here, and do a substitution to find out what is a secant theta and what is cosine theta. So our final step should be negative 3/16 times the opposite of the square root of 4x squared plus 9 all over 3 minus 3 over 4x squared plus 9 plus a constant. I'm going to distribute everything, so all my terms are going to be positive, and with 4x squared plus 9 over 16 plus 9/16 4x squared plus 9 plus a constant. That's a plus 2. I'm going to try to write this a little bit bigger so you can see what I wrote. 4x squared plus 9. Sorry about that. That's the final answer. So as you can see, these problems aren't that difficult. It's just a lot of bookkeeping, as I keep saying. Here's another problem. I'm probably going to pause this one and let you work it out and see if we have the same answer. I will get you started saying that a is equal to 5, u is equal to x, and you're in the form of a squared minus a u squared. So pause the video, and then hopefully you'll come back and see my work. Okay, so you've had some time to work out the problem. Hopefully you got the same answer. I'm going to say that a is equal to 5, u is equal to x. This is in the form, as I said before, is a squared minus u squared. Therefore, x is equal to 5 sine theta, or sine theta is equal to x over 5. That allows me to build a triangle that's over here, which we will use later on this problem. If x is equal to 5 sine theta, then dx has to equal 5 cosine theta d theta. I do a substitution where I see dx. I put my 5 cosine theta d theta. I just put in the numerator instead of just having 1 there. It didn't make sense to write it over here on the right. X squared is 5 sine theta squared, which gives me 25 sine squared theta. I do another substitution here in the square root. I get 25 minus 25 sine squared theta. I factor out a 5 because 25, I factor out the 25 and the 25 comes out as a 5. These 5's cancel. So that gives me cosine theta d theta all over 25 sine squared theta. Instead of 1 minus sine squared theta, I write it as cosine squared theta. That simplifies to a cosine theta because the square root of cosine squared theta is just cosine theta. These cosines cancel out, leaving behind 1 over 25 times the integration of 1 over sine squared theta. We don't like to write things as that, 1 over sine squared theta, so we rewrite it as cosecant squared theta. Sorry, hit the button there. So we have 1/25th of the integration of cosecant squared theta d theta. That's an easy integration. You should know that as a minus 1/25th cotangent theta, going back to our triangle for substitution, and that is all she wrote. And that's an acceptable answer. Here we are on the last problem again. I'm going to be quiet for a second, let you work this out, and hopefully you'll get the same answer. And I will go over it like I did in the previous one. Okay, we're going to finish up this last problem, and that'll be the end of this section. So here's what I have. I have a is equal to 1 and u is equal to 2x. This is in the form of an a squared minus u squared. That's what I'm doing here. So it's in the form of an a squared minus u squared. I then say that 2x is equal to sine theta, because it's, remember, u is equal to a sine theta, u being 2x, a being 1. I rearrange this to be x equals 1/2 sine theta. So I take the derivative, I get dx is equal to 1/2 cosine theta d theta. I build my triangle on the right-hand side, theta, there's my 2x1, and again, this is the part that's over here that we did the substitution for. Everywhere I see a dx, or everywhere I see an x, I replace it with 1/2 sine theta. I square everything. That's this here. Dx becomes 1/2 cosine theta d theta. So my next step is I'm going to take this 1/2 and I'm going to put it on the outside of my integration. 4 times 1/2 squared, that's 4 times a quarter, which is just 1. That's why I have a 1 minus sine squared theta here, cosine theta. From there, instead of writing it as 1 minus sine squared theta, I use the Pythagorean identity, and it becomes cosine squared theta. So I have 1/2 times the integration of the square root of cosine squared theta, cosine theta. Cosine squared theta, the square root of cosine squared theta is just sine theta. That's what I have here. So this is this piece here. And then I combine them to get 1/2 times the integration of cosine squared theta. I'm going to rewrite that using the double angles. So I have a 1/2 times 1 plus cosine 2 theta. That again is on your sheet. The 1/2 comes on the outside, give me a quarter. So I have 1 plus cosine 2 theta. When I integrate that, the 1 becomes a theta. Cosine 2 theta, when I integrate that, becomes 1/2 sine 2 theta. There's my quarter on the outside. And don't forget to put a plus c. Here's a note that I need to remember, that sine 2 theta is equal to 2 sine theta cosine theta. That's on your sheet that I'm going to provide on the test. So when you're in trouble, I can't integrate 2 sine theta. I can't look at this triangle, oh, 2 times this theta would just be 2 times this. Not necessary. All right. So you have to be careful how you're doing this. I'm using some identities to help me get out of the problem of having 2 times the theta. So now I rewrite it as 1/4 theta, a half. But instead of writing this part out like this, I wrote it out as this. So again, instead of having sine 2 theta, I have 2 sine theta cosine theta by substitution of using this part here. Whoops, using that part there. I clean that up and I get 1/4 times theta plus sine theta cosine theta plus a constant. I go back up to my triangle to find out the parts. Hopefully I have that written down. And then I do my substitution and I clean it up, and that's my final answer. Again, that's everything for section 7.3. I apologize for the video being in 2 parts, but unfortunately there was an error. There's a technological error, and I had to do it in 2 parts. Thank you very much, and I look forward to seeing you in class. The next section will be section 7.4.